Yeah, first of all, thank you very much, Akash and Wolfgang, Katerina, for inviting me to give this talk here. So indeed, I'll be talking about spin current in various forms. Hopefully, so my goal of today is of this talk is to introduce a little bit of the physics that then the later speakers can expand upon. So I'll be talking a little bit about exotic spin currents. That will be kind of the topic of SOTA K in a broader sense. I'll be talking about magnon phonon interactions. That's the next talk, and also about magnon spin transport. But I won't say much about details there. But I want to put it all in a broader framework. Yeah, so it's also a pity that I'm not able to go to Mainz, even though it's only a couple of hours away, and I would have loved to go there, but that's unfortunate. But anyway, so spin current and all this, guys. So I'm going to talk about spin current. So I would like to, since this is a conference putting basically superconductivity and spintronics together, roughly speaking. I want to give a long-term motivation of just looking at spin currents. So the idea is, so you're familiar with superconductors, where you have a dissipationless charge current between two, let's say, normal leads, in the sense that you have an Ohm's law where the resistance that's independent of the length of the superconductor. So there's no voltage drop across the superconductor. However, this is still so far restricted to below room temperature. And then what spintronics might contribute is by instead of looking at charge currents, looking at spin currents. So having a similar setup with some leads that for spin, I'll be talking in detail about what those leads could be. And then in between, some dissipationless spin conductor. Now that doesn't exist yet, or may not exist at all, but that's at least something to strive to work towards too. And so the idea is to somehow replace this Ohm's law for charge current with some dissipationless version of spin current, and this might happen then above room temperature. And the reason why that might happen above room temperature is that we'll be dealing with magnetic materials, and in magnetism the energy scales are set by the exchange interaction, which is a very strong interaction. So this might occur above room temperature. So this is kind of the mental, let's say the frame that you should have in mind for let's say the broader goal of what I'm talking about. So spin currents. So before we go into spin currents, it's maybe good to ask a basic question, namely, what is spin? It may be a little bit late for some of you in the audience, also for me, working in spintronics for more than 15 years, if I'm correctly. So it's still never too late to ask the question, what is spin? So I'm not going to answer this question in great detail, because luckily if you Google this, you find a paper with the title, which is the same as this question. It's a relatively old paper. It was pointed out to me. I should give full credits for actually making this slide to Simon Stripe, who pointed this paper out to me. And roughly the definition of spin is it's the part of the angular momentum that is independent of the origin of the coordinate system, right? So it's kind of an intrinsic rotation, say. And this is kind of this independence of the coordinate system is important, because this means you can transport it from, let's say, A to B, or from one lead to another lead. Now, the reason I'm bringing this slide up, so I'm not going to go into detail into what precisely this question and what this answer means. It's a very nice paper to read. The reason I'm bringing this up is that Simon has also recently submitted a paper to the submitted a paper. It's on the archive. The reference is in the bottom right. Let me actually switch to a laser pointer. So it's in the bottom right here, where he points out that there may be some potential issues with spin and spin currents in relation to real versus pseudo angular momentum. So some recent works have been discussing, for example, angular momentum of orbital angular momentum of magnons or phonons, and most of the time this is pseudo angular momentum, whereas what I'm going to talk about is all about real angular momentum, real spin angular momentum. So if you want to learn more about that, I encourage you to read both of these papers. Now, so having said that spin is independent of the coordinate system, it makes sense to think about transporting spin. And so I'll be going to various developments in transporting spin. And I will start with some general remarks, and then I'll go briefly over electronic spin transport. So that's, I would say, old by now to some extent. So looking at spin transport in ferromagnetic metals has been going on for several decades. More recent development is spin transport through electrically insulating magnets, or magnetic insulators. And if time allows, I'll be saying a little bit about my own work on phonon spin transport, just because it's not really covered in great detail in this session. So pure phonon spin transport. So magnon phonon spin transport is the next talk, but pure phonon spin transport is not discussed in this session. So I'll take the opportunity to say a little bit about that towards the end of this talk. So I'll start with some general considerations. So I think it's also good to imagine, first of all, that the most ideal situation, which does not exist in the world that we live in, but which would be somehow the most ideal situation of spintronics, so to say. So this would be spin transport in a world where spin would be purely conserved. So then you could make a reservoir of spin. So this reservoir would be characterized by a spin chemical potential, so a vectorial quantity. So there's a indicated with mu s on the left there for the left reservoir. There's a similar quantity for the right reservoir. So these spin accumulations would then be given by derivative of the free energy with respect to spin. So this is the thermodynamic definition of chemical potential for a conserved quantity, if you will. So you could then build these reservoirs in equilibrium, take these two spin accumulations to be different, and then connect them with some spin conserving material. And so in this spin conserving material, there's one equation that then holds, which is namely a continuity equation for spin. And this then defines a spin current in a certain way. And how this spin current is then expressed depends on what kind of spin conserving material you're dealing with. So this would be the ideal situation. So I want to discuss, so this is very abstract, of course. I would like to discuss two limiting cases, still kind of imagining that spin might be a conserved quantity. So one is purely electronic spin transport, and the other one is where this is all going on in magnetic insulators. So let's first go to the electronic version. So then we imagine that there's some electronic reservoir with a finite spin accumulation. So again, this is, I'm imagining now for the moment that spin is conserved. So where the spin accumulation is coming from, I don't care about. I imagine that I can build an equilibrium reservoir with a finite spin accumulation. There's an electronic reservoir on the right. So these two spin accumulations are different, and I connect them with a paramagnetic metal. So what then happens is that there will be a spin current, a purely electronic spin current going from left to right, carried by electrons, right? So that's kind of what happens then. So the upper electron, so if this would be pointing in the, let's say the positive z direction, both these spin accumulations, and would be different only in magnitude, not in direction. And you would have the up electrons going to the right, the down electrons going to the left, and that would be your pure electronic spin current. And since this is a paramagnetic metal, there's no charge current in this case. So what are now the equations to describe this? So again, there's a spin continuity equation. And then since this is electron spin transport, it's the spin transport is diffusive. So this is an ordinary paramagnetic metal, no superconductivity, no ferromagnetism, no other, well, it's just ordinary, not exotic in any kind. So then the, let's say, constituent equation that you need to derive an equation for a closed equation for the spin density in this paramagnetic metal would be that just a diffusion type equation where you express the spin current in terms of the gradient of the spin density. And this can then be expressed in terms of the gradient of the spin accumulation in this paramagnetic metal. So just to point out a couple of issues that I should have pointed out also in the previous slide. So this is all very general. This paramagnetic metal is isotropic. I assume it to be isotropic. So there's a vectorial spin direction. So this current both has a, so the spin current here is a tensor. It both has a, let's say, a spin direction, which is indicated with the arrow, and it also has a spatial direction, which is indicated with the boldface vector. But in principle, it's a two-component. So it's a two-component tensor. And so also here, this gradient refers to the spatial direction. The arrows refer, the vector head arrows refer to the spin polarization. And so there's a couple of important concepts here already on this slide. So one is the spin diffusion constant coefficient. And the other one is the spin conductivity, and they're of course related by an Einstein-like relation that I don't describe here. So this equation is kind of all you need to describe the spin transport in this paramagnetic metal, and then you need some boundary conditions that describe how the what happens at the interface between the reservoirs and the system that you're interested in. And this could, for example, be interface spin resistances of this kind, where you say that the interface spin current is proportional to the drop of the spin accumulation across the interface. So this would be kind of the complete picture of electronic spin transport in the ideal world where spin is conserved. I want to point out one thing that maybe not everybody knows, not even the experts, which is that even if this system would be clean, so wouldn't have any impurities and also wouldn't have any phonons that are relevant, and still the spin transport would be diffusive because of interactions between the electrons. So up and down electrons scatter off each other, and this always makes the spin transport diffusive in principle. And so this phenomena is called spin drag. So only at very low temperatures will this vanish. Okay, so this is kind of the electronic spin transport in the ideal world. Now I want to look at spin transport in ferromagnetic insulators in the ideal world. So again, assuming that spin is conserved, and now my reservoirs are just very large magnetic insulators, and this is actually all at 0 temperature. So let's assume that my reservoirs are now magnetic insulators at 0 temperature. So this one is pointing in the direction of this arrow here. So let's say up. This one is at a slightly different angle here. And then in between, I also have a magnetic insulator. So these are kind of the reservoirs that are very large pieces of material, say. And then in between, I have a magnetic insulator. And now the magnetic insulator is typically described by something that's called the Landau-Lifshitz-Gilbert equation. But since for the moment spin is conserved, this is the Landau-Lifshitz equation. And furthermore, since spin is conserved, I don't have any anisotropies or anything. So I only have exchange interactions. So if you are in that situation, you can actually write the Landau-Lifshitz equation as a spin continuity equation, which then defines a so-called exchange spin current. So this is a spin current that is carried by the magnetic moments in a magnetic insulator, by the spin in a magnetic insulator, once you have twisted the magnetic order. So this gives a interface spin current. And then to describe the full spin transport through this system, you need some interface exchange coupling that, let's say, so these are the boundary conditions are now some interface exchange coupling between the, let's say, this reservoir here and the moments in the magnetic insulator at the boundary, and the same on the right. So then you force this material in between in a twist, and then it carries a exchange spin current. Now you may wonder, is this a real spin current? Should I really discuss this spin current on the same footing as the previous electronic spin current? So these are all kind of very valid, let's say, concerns. I'm not going to discuss them in detail here. So I think there's a nice paper that discusses these various aspects and differences between such exchange spin currents and electronic spin current. I do want to point out, using this example, one crucial difference between charge and spin current. It doesn't play a big role in my talk, but what is important, what is an important difference between spin currents and charge currents even in this ideal world where spin is conserved, is that a spin current is actually even under time reversal, because it deals with an angular momentum that moves. So you have a velocity times an angular momentum, and if you change the arrow of time, so to say, both of these quantities change. So a spin current doesn't change sign under time reversal, which means that they can exist in equilibrium, and you might consider this an equilibrium spin current. So there are other examples of equilibrium spin currents in strongly spin orbit coupled systems, for example, electronic systems. I won't say much about it, but at least it's something to worry about whenever you discuss spin currents, whenever you're dealing with spin currents. Now, this is the ideal world. So now I'm moving to the real world. So again, first, so how does this now work in the real world? So in the real world, there is no equilibrium spin accumulation. So in the real world, spin transport is often actuated by a non-equilibrium spin accumulation. And there are several ways to make such non-equilibrium spin accumulation. So this is kind of the first way that it was established, I think, historically in the field of spintronics. And so, so now I'm going to talk a little bit about how that works and what the lead actually is. So in practice, what you often do to establish a electronic spin accumulation is to drive it with a charge current from a ferromagnetic metal. So in this setup, I've now removed one of the leads. So in this setup, you can imagine that the ferromagnetic metal now takes the role of the lead. It's interfaced with a paramagnetic metal. And then if you drive a charge current through the system, then the asymmetry between up and down conductivities, where up and down refers to the direction of magnetization in a ferromagnetic metal, actually injects a non-equilibrium spin current, non-equilibrium spin accumulation in the paramagnetic metal. So since spin is not conserved anymore now, you have to augment the spin continuity equation with a spin relaxation term, for example, of this kind. And you still have the constituent equation where spin current is diffusive. I've removed the vector head on the spin polarization, since I'm now looking only at the spin polarization along the direction of the magnetization of the ferromagnet. So these two equations combined in the steady state, they give rise to a length scale over which the spin accumulation decays exponentially. And so this length scale is given by this expression in terms of the spin diffusion length and this relaxation time. So if this relaxation is not there, if this time is infinite, then also the spin relaxation time will become infinite. So if you solve this type of equations at such an interface with appropriate boundary conditions, for example, continuity of spin charge current, some interface resistances perhaps or not, then you find these kind of pictures where you see the spin accumulation here expressed in terms of the difference between up and down electrochemical potentials. You see such spin accumulations build up near the interface. So this spin accumulation is now only there if you drive a charge current. So in the real world, where spin is not conserved, you can only establish such a spin accumulation by driving the system out of equilibrium. So you're always dealing with non-equilibrium spin accumulations. But nonetheless, over this length scale, so this exponentially decaying, you see this exponentially decaying signal here, which also means that the spin current decays exponentially. But nonetheless, over this length scale, you establish you can establish spin accumulations and spin currents in paramagnetic metals. So this is kind of first example of getting a spin current into something that is not that is not spin polarized by itself. This is, however, not such a nice. Well, experimentally, this may be annoying because this circuit also has charge current flowing through it, and ideally, you would like to look at the pure spin current rather than a spin current that's accompanied by a charge current. So one way of, so how do you actually get rid of this accompanying charge current? So one way to do this is to go to a situation. I'm still talking now about metals and semiconductors, so about electronic spin current. So one way to go about this is to go to a non-local setup where you drive a charge current between two terminals, let's say on top of a paramagnetic electronic system, so a metal or a semiconductor. So this now injects spin current. So if you drive a charge current here, this injects spin current across this interface, very much with the same mechanism that I discussed on the previous slide. However, so the charge current flows here. The spin current, so the non-equilibrium spin accumulation may actually diffuse to the right as well, and is not accompanied, at least not accompanied by a charge current, at least not a large one. And then can be picked up in a reciprocal process with a similar setup using one ferromagnet. And so you have an injection of spin current and a detection of spin current, where both of the times this injection and detection is done by converting it using, in this case, ferromagnets to an electronic current. Okay, so this is, but nonetheless, apart from that, apart from this four-terminal setup, this system is still characterized by a spin diffusion equation of the kind that I showed before. And so you'll find with relaxation, so you'll find a electron spin accumulation that decays exponentially towards the right here, for example. You can define a non-local resistance that characterizes the spin transport that will be decaying as well, exponentially over the length between the injector and the detector in this case. So measuring this non-local resistance for different distances between injector and detector allows you to measure the spin diffusion length. And if you do that, then you find length scales on the order of several nanometers for metals with, let's say, strong spin orbit coupling. Or you could find length scales on the order of micrometers for very clean, very pure semiconductors or semi-metals. So I think the record for electronic spin transport is currently held by graphene, if I'm not mistaken. But I guess this afternoon or tomorrow afternoon we'll hear more about that. Okay, so this is kind of how spin transport in electronic systems typically works. So I want to end the discussion of electronic spin transport by mentioning some versions of electronic spin transport that are more exotic than this. So in this setup that you see here before you, you're really dealing with spin transport carried directly by the spin polarized electron. So it's to some extent the most straightforward way of spin transport. The question is, can also electronic systems, can they carry spin in a more exotic way? And the answer, well, exotic is of course could mean anything, but in this case I mean specifically not directly with their own spin, but in a different way, with another degree of freedom that emerges from the electrons. And the answer to that question is yes. So you could actually transport spin through electronic systems using electron vorticity. And so the schematic picture of what then could happen is the following. So imagine you have some electronic system in which the electrons can form vortices in one way or another. I will say more about it in a second. Then you have a lead that injects electronic spin into that system and extracts it somewhere else. So that allows you to measure a spin current in for example, using the setup that I showed previously. However, in between, the spin is not carried by, the angular momentum is not carried by the spin of the electrons, but by vortices formed by the electrons. So this could happen in superconductors. So that's why I'm bringing it up, since there may be people working on superconductivity listening to this talk. So this was proposed by Sekwon Kim and collaborators, where they considered how vortices in superconductors in this setup could mediate non-local spin transport. So injection of electronic spin, some conversion process at the interface, and then this spin is absorbed as a vortex in a superconductor. So it really is superconducting vortex. So this is one example of electronic spin transport that doesn't actually, I should perhaps say electronic angular momentum transport that doesn't use the intrinsic spin of the electrons. Another example is viscous electron systems. So there are electron systems that have gained attention recently that are hydrodynamic, meaning that the electron-electron interactions are much stronger than the other interactions. And then you should describe the electrons with Navier-Stokes-like equations. So they become a viscous fluid. And in such a viscous fluid, you may also have vortices. So this was considered by us also by Matsuo and collaborators. So looking at how spin transport in such a viscous electron system works, and you find that especially in spin orbit coupled system, there's a large coupling between spin density and vorticity, so between vortices, and that may also mediate spin transport. And yes.
Can you pause for a question? Would it be okay?
Yeah, please, please.
Okay. Daniel Komsky has a question, so I will allow you to talk now, Daniel. So please unmute yourself and you can ask the question live.
Actually, I have a question about this ideal situation with non-dissipative spin current, which you started with, and you have on the left end spins looking, for example, up, on the right end spins looking at certain angle and certain spin rotation. That's indeed what people call sometimes spin current, and mathematically it's really very similar to superfluid current or current and superconductivity without dissipation. Now, simply just maybe a bit naive question. Suppose I have this situation, it's like a rod of ferromagnetic material, and I start to rotate magnetic field at the left end so that the spins at the left ends are rotated. And it looks like, in ideal case, this spin rotation would transfer along this rod to the right end. Now, probably it would not be good for ferromagnet, because in ferromagnet, magnon spin wave spectrum starts quadratically, omega like u squared, and that violates Landau criteria of superfluidity. But for antiferromagnet, with linear spectrum of magnons, it looks like naively Landau criteria of superfluidity is always fulfilled. So would it really work exactly the same way as just a real non-dissipative transport in superconductors? What are the weak points? Where is the loophole in this?
Yeah, I think so.
Once again, the rod, ferromagnetic or antiferromagnetic rod, and I start to rotate magnetic field at the left end. What would happen at the right end, ideally?
So you're talking about this picture, for example. So I think, yeah. So let's say in the ferromagnetic case, it's not really so it's not a U1 symmetric system. So in the ferromagnetic case, you would have to do things with an easy plane ferromagnet, for example, that confines the spin in the plane. So if you do this with a ferromagnet, then you will get something. At some point, it will start unwinding by going by pointing up, for example. So there's one issue related to confining the magnetic order in one plane. That's why it wouldn't work in this ideal case for a ferromagnet. So that's one situation. For an antiferromagnet, I think you would still need to have an external field everywhere to confine an easy, to also define an easy plane to really have superfluid-like transport. So I don't know if I completely answer your question with that, but there are just issues with kind of unwinding of this texture in between, why it doesn't work.
So I think once again, for ferromagnet, even for easy plane ferromagnet, probably it wouldn't work because magnon spectrum is quadratic, and that's violate Landau criteria of superfluidity.
No, in an easy plane ferromagnet,
if spin magnon spectrum is linear, then at least there is no problem with Landau criteria. Maybe there are some other problems. There should be some loophole in this reasoning, but what could indeed hinder this kind of naive experiment? Once again, rotate magnetic field at the left end, and signal would be transferred to the right end, because mathematically it's indeed identical to.
I think it would actually work. So I think even for the ferromagnet, it would work with easy plane anisotropy up to some point, because in an easy plane ferromagnet, the spectrum is actually linear also in the symmetry broken phase. If your anisotropy is stronger than the external field, say.
Okay, sorry for interrupting the discussion, but I think we can maybe continue with it. the detailed discussion, the coffee break. So maybe Rembert, you can proceed with the topic.
Yeah, actually, maybe this is also a better discussion if I move towards the blackboard in my, my office.
Yeah. Thank you for the question. Thank you for the discussion.
Thank you for the question. I will. We can discuss later. I will be for surely at the coffee break. Yeah. So just to wrap up the electronic spin transport. So there are more exotic ways of transporting spin than just actually transporting angular momentum, I should say, than just using the spin of an electron, namely via the vorticity. So this was kind of the first part. I would like to continue with explaining how this would actually work in electrically insulating magnets. And in particular, I would like to kind of go towards electrically controlled spin transport through such systems. Just to be able, well, first of all, it's kind of nice to interface. So the main reason is this, that you would like to still interface your spin transport system with something electronic, so that you're in the end, in terms of an application, are able to connect it to, let's say, ordinary present-day devices. So that's why people are focusing on this electrically controlled spin transport. So the question is now, how would you now get a electronic spin current into an insulator? And the answer of that is using actually the spin Hall effect and its inverse. I'm not going to say a lot about the spin Hall effect. I just want to discuss the phenomenology of it, because it's what people use nowadays routinely, actually, to inject and detect spin currents into and out of every insulating system that you can possibly think of, it seems. And so the idea of the spin Hall effect is that you kind of have a charge current in a certain direction, and then because of spin orbit coupling, large intrinsic spin orbit coupling, you set up a transverse spin current. So let's say one projection of spin goes to the left, the other projection goes to the right, and it sets up a pure spin current, so not accompanied by charge current, in this picture to the right. And so the Onsager reciprocal of this is the inverse spin Hall effect. Now there's a lot more to be said about the spin Hall effect and its inverse. There's many caveats to be made about lack of spin conservation, about whether you can define spin currents, etc. But we can discuss them later if you will. So a typical material that people use nowadays is platinum, it seems. That's the favorite material. And what is important for our discussion is that a spin Hall effect establishes now a spin accumulation. So if this would happen in a metal that's kind of stops here, then you build up a spin accumulation that decays away from the interface exponentially over the length scale, the spin diffusion length that I discussed previously. Now, so why is this a useful effect? It's a useful effect because it allows you to set up a spin accumulation near an interface between a metal and something that does not transport a charge. So, for example, a magnetic insulator, by driving a current tangential to the interface. So in this setup, the charge current is, let's say, going into the screen, and then you set up via the spin Hall effect a spin current in this direction, so towards the interface. And at the interface, this sets up a spin accumulation, and this spin accumulation would like to relax, so the spins would like to flip. And in doing so, they can actually give their angular momentum, their spin angular momentum, to the other side of the interface. So if this is a magnetic insulator, what could happen is that an electron comes in, flips its spin, and then this flip spin, this angular momentum that's deposited at the interface, is absorbed by a spin wave, so by a fluctuation in the magnetic order. In let's say the very simplest, to some extent the simplest example of what could happen here. And this, so then you set up a spin current into the magnetic insulator. You could also do this with a temperature difference. So this is referred to as the longitudinal spin-Seebeck effect, pioneered by the group of Saito. But I will mostly talk about electrically driven spin currents. Okay, so to set this up, you need some material with large spin Hall effect, some interface exchange coupling that actually couples this spin accumulation to the moments on the right. So you need this interface exchange coupling, because otherwise this the non-equilibrium spin accumulation that you establish here will not relax into the magnetic insulator, but will relax by spin-orbit coupling by itself. But this is how you inject a spin current into a magnetic insulator. So now to discuss spin transfer, so I want to put it on the same footing at the previous discussion. So instead of having now, so previously I discussed the magnetic insulator connected to two large magnetic insulators that serve as a reservoir. So now I want to kind of enrich this picture by considering a heavy metal with a spin accumulation established by the spin Hall effect. There's usually only one direction of spin accumulation relevant near the interface. Another heavy metal to detect the spin current, and then in between a magnetic insulator. So we have some spin continuity equation in a magnetic insulator, but in principle there's spin relaxation, and we also need to worry about boundary conditions. So does this work actually in practice? So the answer is yes. So this was first done in the group of Bart van Wees by Ludo Cornelissen. So the schematic of what he does is in this nice picture. So you have two platinum strips with a magnetic insulator in between. Charge current gives rise to a transverse spin current that's absorbed by spin waves. And then at the other interface, you have a reverse process that sets up a charge or a voltage in this setup. And so this is how the device actually looks. So these are the platinum strips. You drive a charge current here, and detect a voltage there, and that gives rise to, this allows you to define a non-local resistance as a ratio. And this non-local resistance decays exponentially, which is actually a measure for the spin diffusion length, now not of the electrons, but of the magnons in the magnetic insulator. So one way to think about it is in terms of a non-equilibrium magnon spin accumulation. So magnons are not conserved, but are nearly conserved. So this allows you to introduce a spin accumulation. And then this spin accumulation, like in the electronic case, decays exponentially. And in the experiment, it's actually found that this diffusion length is 10 micrometers. So that one of the nice things about this experiment is that it beat all electronic systems, or at least rivaled the record electronic system in its first attempt. So I won't say much more about the experiment. So there's a talk at 12:30 by Sebastian. Just again to put it on the same footing as my previous discussion. So we have some spin continuity equation that's augmented by a relaxation term. I haven't said it before, but of course this kind of assumes that spin is still a relatively slowly varying quantity, such that so this decay term shouldn't be the dominant one, of course. And then the constituent equation is a diffusion equation for magnons in this case, and in terms of a chemical potential, non-equilibrium spin accumulation. This defines then a magnon diffusion coefficient, a magnon spin accumulation, a magnon spin conductivity, and with some boundary conditions, you can now solve or describe the entire spin transport. And of course, the characteristic length scale that I talked about before is now the magnon spin diffusion length. So I want to point out, maybe this is sometimes this picture leads to some confusion. So I want to point out one thing, namely that you should really think about this type of spin transport as spin transport as a biased cloud of magnons that are already there because of thermal fluctuation. So this process doesn't work one by one, meaning that you don't really excite the spin waves that are not there yet. So it's not let's say a process of spin excitation, so to say. It's more like a process of biasing magnons that also happens in linear response even. And actually all these experimental results were in linear response. So that's kind of an important remark because I noticed that there's sometimes confusion in the community about this. Now to go back to spin superfluidity, also the question was kind of in this direction. So how would spin superfluidity now work? Electrically controlled spin superfluidity, that is. So instead of looking at magnon transport, you can put a easy plane magnetic insulator in between. And this easy plane order you can set into rotation by injection of spin current. So this easy plane magnetic order can twist under the influence of biasing. And this setting up of this twist actually mediates a spin superfluid current. So it's an exchange current in the same way, But since this is now confined to the easy plane, the only component that you should worry about is actually the out-of-plane component of the spin current, and that's proportional to a gradient of the angle phi, and this angle is just a rotation angle of these spins in between. Now again, there are still non-conserving effects in the real world. So one of them is just dissipation of the magnetic dynamics, and that leads to algebraic decay of the spin superfluid current. Because of, well, you can describe this, for example, with Gilbert damping. There's also a lower critical current typically because of in-plane anisotropy. And so spin superfluidity is always accompanied by a lower critical current and also an upper critical current, because at some point this texture will start winding out of the easy plane, and that sets an upper critical current. Okay, so this is how spin superfluidity would work in principle. If you have an easy plane ferro, or this could also be an anti-ferromagnet. Now I want to end the discussion of magnetic insulators with more exotic forms of spin transport through insulators. So in principle, this setup of having a metallic lead with a large spin Hall effect, such that you're able to inject a spin, well, to establish a spin accumulation at an interface with something else, some other material, allows you in principle to think about spin transport through any system that has some magnetic properties, or even non-magnetic properties, as I'll discuss towards the end. So there are several examples that are being discussed in the literature. This list is probably not complete, so I hope I don't offend any of you. So this is a picture of a publication by Jaroslav and collaborators. So they've been pushing the idea of topological transport. This is not necessarily spin transport, but their idea is that, and Sotake has actually also worked on this a little bit. So their idea is that you can also transport, that you can actually use the topology of the magnetic order parameter to make conserved quantities that are conserved because of their topological properties. For example, a winding number. So a winding number is always conserved regardless of dissipation in the magnetic system, just because it's topological property. And then such a winding number, if you define it locally, also obeys a continuity equation, and you could imagine transporting it and then injecting and detecting it electronically. So the work of Jaroslav has discussed several examples of this kind. So this topological transport has been known in other systems, but is not considered until Jaroslav's work in magnetic systems. So the second thing is you can also think about more exotic magnets. So the field of quantum magnetism is huge, and there's no reason why you could not, in principle, think about or even experimentally probe the spin conduction properties in this setup with metallic contacts that I've discussed previously. And so there's one example, quantum spin liquids, that will be the talk of Sotake after, well, I think at noon, if I'm not mistaken. So there are experimental examples of spin currents carried by spinons and even by paramagnetic GGG in the CITO group. Anti-ferromagnets have been studied experimentally in the group of Matthias Klauwe and Wei Han. And van der Waals magnets are yet another example. And probably there are many more examples that I'm skipping here. So you feel that I neglected you, please bring it up during the question hour. And again, to remind you, so Sotake will talk about these more exotic forms of spin transport. So I'm nearly at the end. I want to, in the end, discuss one example of spin transport through actually insulators that are not magnetic, which is phonon spin transport. And so phonon spin transport, so phonons actually also can carry spin. So if you think about the motion of atoms in solids, you can actually decompose this, let's say, rotational motion, or any motion you can decompose in a translation, vibration, and rotation of this kind. So if you decompose the angular momentum, you can decompose into a global rotation of the system and into, let's say, in this pictorial sense, the atoms rotating around their equilibrium position. And so this would correspond to the case of phonon spin. And so does this phonon spin really exist? So experimentally, it has been shown to, it has been measured actually in a setup using YIG, yttrium iron garnet. This is the most commonly used magnetic insulator. And they have done this by making use of the hybridization in this system of phonons and magnons. So there's an avoided crossing because of the coupling between a phonon branch and a magnon branch. And where this coupling is, you can actually tune with a magnetic field. Now, if you then make a system with a magnetic field gradient, then you can, by using this magnetic field gradient, you can actually excite a pure magnon on one side of the system. And if this magnon, if the spin wave travels through the system, it's converted into a pure phonon. So going from here to here, say. And then if you measure then the spin of the phonon, you can measure whether the spin of the magnon, which you know is h bar, is actually completely transformed into the phonon spin. And so this was done by BLS experiments, if I'm not mistaken, and indeed showed that the phonon spin that was measured after this conversion process is indeed h bar. And so phonons carry a spin h bar like photons actually. So circularly polarized phonons are very much like circularly polarized light. So I will not say too much about this anymore because as the next talk will actually be about the strong magnon-phonon interaction. I will just end by saying that you can in principle use these phonons to mediate spin currents as well. So you could imagine that I have a reservoir of a magnet with finite magnon spin accumulation. So this magnon spin accumulation would then be established by driving a spin orbit coupled metal adjacent to it. But so let's imagine there's a magnet with a non-equilibrium magnon spin accumulation on the left, on the right as well. And then because of magnetoelastic coupling at the interface between the magnet and the non-magnet and the magnetoelastic coupling in the bulk here, you actually get a spin transfer from the left to right magnet, so spin currents flowing from the left to the right in this system due to magnetoelastic interactions. We'll skip this slide, but so there's an experiment done not in this incoherently driven regime, but in the coherent regime, looking at coupling between two ferromagnets with a magnetic insulator in between. And what they found were these resonances due to that kind of demonstrated that the coupling between these two ferromagnets is mediated by phonons, by phonon angular momentum currents, spin angular momentum currents. And so if you actually calculate these spin currents and look at how they decay with the length of the insulator in between, you actually find that so that you can define a certain spin conductivity. You find there's an exponential decay of the spin conductivity with the distance, with the length of the system in between the leads. And if you plug in the YIG and GGG parameters, you actually find that this decay length is much larger even than the magnonic system, can even reach 1 millimeter. Okay, so phonon spin currents seem to be very promising for giving long-range spin currents. Okay, so here this is where I'll end. So I'll just flash my take-home message. So I started out by discussing the ideal world. So reservoirs with a finite spin accumulation and something in between that conserved spin. So this does not work, of course, in the real world. But the message is that I think it's kind of known now how to make these reservoirs electronically, at least, so to connect them to electronic systems to measure electronically the spin currents and to inject them. We've seen many examples of systems that nearly conserve spin, and so we've seen the spin diffusion length going from electrons, where it's nanometers, to magnons, where it's tens of micrometers, to phonons, where it's millimeters. And so I hope that many more materials, so there's a large zoo of materials which apparently are very good spin conductors, and I hope that many more will follow and will be demonstrated experimentally to be able to conduct spin. And I hope that this record spin diffusion length will still be broken in the near future as well. So thank you for your attention.